Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the area of this trapezoid ABCD. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So, we start with the first question. In the drawing, we have a circle that is inscribed. We have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length. This is side DC that equals to 7 over x units in its length. This is angle BAD that is a right angle. This is angle ADC that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. Here we have, this is quadrilateral ABCD, and because of the fact that side AB is parallel to side DC, this quadrilateral ABCD is defined as a trapezoid. And the two parallel sides, that is to say side AB and side DC, are defined as the bases of this trapezoid. And what is the area of this trapezoid ABCD? The area of this trapezoid ABCD equals to the sum of its two bases, that is to say AB plus DC, times the height that is edge over 2. So if we define the base AB as B and the base DC as A, then the sum of the bases of trapezoid ABCD will be equal to A plus B times the height that is edge over 2. So in conclusion, we found out that the area of trapezoid ABCD equals to A plus B times edge over 2. The height edge must create 90 degrees with the two bases. Here you can see that the height edge creates 90 degrees with the base A, with the base B or AB, and it also creates 90 degrees with the base DC. This angle equals to 90 degrees, and this angle also equals to 90 degrees. So in conclusion, the area of this trapezoid ABCD equals to A plus B times edge over 2. Okay. So, first of all, we will define the points of tangencies of this trapezoid ABCD with this circle with letters. We will define the point of tendency of tangent AB with this circle, this point as E. Likewise, we define the point of tendency of tangent. We define the point of tendency of tangent BC with this circle, this point as F. We define the point of tendency of tangent AD with this circle, this point as G. And finally, we define the point of tendency of tangent DC with this circle, this point as H. So here we can implement rule 2 in this drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have this circle, and we have this is the convex point P. From this convex point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule two, PA equals to PB. Repeat again that we can definitely implement all two in our drawing. Why? Because in our drawing, if we focus on this convex point A, from this convex point A, we have two tangents to this circle, tangent AE and tangent AG. According to all two, they are equal to each other. That is to say, AE equals to AG. So if we define the length of tangent AE as y, then the length of tangent AG must be also equal to y according to rule 2. Likewise, if we focus on this convex point B, from this convex point B, we have two tangents to this second, tangent BE and tangent BF. And according to rule 2, they are equal to each other. That is to say, BE equals to BF. So if we define the length of this tangent BE as Z, then the length of this tangent BF must be also equal to Z according to rule 2. Likewise, we focus on this convex point C. From this convex point C, we have two tangents to this second, tangent CF and tangent CH. And according to rule 2, they are equal to each other. That is to say, CF equals to CH. So if we define the length of this tangent CF as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, we focus on this convex point D. From this convex point D, we have two tangents to this second, tangent DH and tangent DG. And according to rule 2, they are equal to each other. That is to say, DH equals to DG. So if we define the length of this tangent DH as T, then the length of this tangent DG must be also equal to T. In the next step, we define the length of this side AD of trapezoid ABCD as A. So AD equals to A according to our definition. Likewise, we define the length of this side BC of trapezoid ABCD is B. So BC equals to B according to our definition. So, what is the value of side AB plus side DC? AB plus DC. AB equals to Y plus Z and DC equals to T plus M. So in total we actually found out that AB plus DC equals to Y plus Z plus T plus M. What is the value of side AD plus the opposite side BC. AD equals to y plus t and BC equals to z plus m. So in total we found out that AD plus BC equals to y plus t plus z plus m. So we have this expression y plus t plus z plus m. According to the algebraic identity, let's say that a plus b equals to b plus a. We can change the orders of these letters here, and instead of y plus t plus z plus m, we can write down that this expression equals to y plus z plus t plus m. We just change the orders of these letters. So here a b plus bc equals to y plus z plus t plus m, and AD plus BC also equals to y plus z plus t plus m. So those two expressions in the green color, they are both equal to the same third expression, that is y plus z plus t plus m, therefore they are equal to each other. That is to say, AB plus BC equals to AD plus BC. This is equation 1. AB equals to x according to what is given as the equation, so we substitute AB by x plus DC. DC equals to 7 over x according to what is given as the equation, so we substitute DC by 7 over x, and it is equals to AD plus BC. AD equals to A according to our definition plus BC. BC equals to B also according to our definition. So in conclusion, we found out that according to equation 1, x plus 7 over x equals to A plus B. In the next step, we will do a construction, that is to say, from point B we will go perpendicular on DC. Again, from this point B we will go perpendicular on DC. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC, this point is point S. When doing this construction, we created quadrilateral ABSD. So inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Because of the simple fact that the sum of three angles that is 270 degrees plus this angle that is 90 degrees, in total it is 360 degrees. That is the sum of the angles in any quadrilateral. So inside quadrilateral A, B, S, D, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral A, B, S, D is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB equals to X, therefore DS must be also equal to X. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD equals to A according to our definition, therefore BS must be also equal to A. By doing this construction, we can deduce the right triangle BSC. This is the right triangle BSC. This right triangle BSC, the hypotenuse BC equals to B. This is side BS that's equal to A. So what is the length of side SC? From the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. So that is known. The length of side SC is equals to DC minus DS. So SC equals to DC is 7 over X. Minus ds, we just write down further that ds equals to x. So in total, SC equals to 7 over x minus x. This is side SC is equals to 7 over x minus x. So in the next step, I'll copy this right triangle BSC in a new page, and we will implement on this right triangle BSC the Pythagoras theorem. Here by PT is the evaluation for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle BSC that I got from the original drawing. In this right triangle BSC, according to the Pythagoras theorem, BC square equals to BS square plus SC square. This is equation 2. So according to equation 2, BC square equals to BS square plus SC square. the hypotenuse BC equals to B, therefore BC square is B square, and it is equals to BS square. BS is A, therefore BS square is A square plus SC square. SC equals to 7 over x minus x, therefore SC square equals to 7 over x minus x square. So according to equation 2, we actually found out that B square equals to A square plus 7 over x minus x square. So here we will simplify this expression 7 over x minus x square according to the algebraic identity that states that A minus B square equals to A plus B square minus 4 times A times B. So because of the fact that in equation 1 we have the expression of x plus 7 over x, and in equation 2 we have the expression of 7 over x minus x square. We want to turn the expression 7 over x minus x to 7 over x plus x, exactly according to equation 1. And according to this algebraic identity that A minus B square equals to A plus B square minus 4 times AB, we will get that 7 over x minus x square will be equal to 7 over x plus x square minus 4 times 7 over x times x. So 7 over x minus x square equals to 7 over x plus x square, and here we have x in the numerator and x in the denominator, so x will get cancelled. After we cancel the x, this expression will be left only with minus 4 times 7, that is minus 28. Minus 28. So actually found out that the value of 7 over x minus x square equals to 7 over x plus x square minus 28. Now, this expression equals exactly to what we have here in equation 1, 7 over x plus x. Therefore, we can use equation 1 in order to substitute 7 over x plus x by a plus b. So, in this equation 2, we have b square equals to a square, and here 7 over x minus x square according to this algebraic identity is equals to 7 over x plus x square minus 28. So we actually found out that according to equation 2, b square equals to a square plus, we have here 7 over x plus x square, and according to equation 1, 7 over x plus x equals to a plus b. If 7 over x plus x equals to a plus b, it means that 7 over x plus x square will be equal to a plus b square. Therefore, we can substitute 7 over x plus x square here by a plus b square according to equation 1, and we have to subtract also minus 28. So in conclusion, we found out that b square equals to a square plus b square minus 28. So here we'll open the brackets of this expression a plus b squared, and we get that according to this equation 2, b squared equals to a squared plus a plus b squared. A plus b squared equals to a squared plus b squared plus 2 times ab, and we have here minus 28. So in conclusion, we found out that according to equation 2, b squared equals to a squared plus b squared plus 2 times ab minus 28. So here we have b squared on both sides of this equation 2. So b squared will get cancelled. After we cancel b squared, this side of the equation we left with nothing, that is to say 0. And it is equals to, on the other side of the equation, we have a squared plus a squared, that is 2a squared, plus 2ab minus 28. So if we will add 28 to this equation 2, and we get that 0 plus 28 is 28. Is equals to 2a squared plus 2ab. So here we divide this equation 2 by 2, and finally we get that according to equation 2, 28 over 2 is 14. That equals to 2a squared over 2 is a squared, and 2ab over 2 is ab. So in conclusion, actually found out that according to equation 2, a squared plus ab equals to 14. This is according to equation 2. But according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have those two equations. Repeat again that our mission is to find out the area of this trapezoid ABCD. So according to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD is equals to the sum of its two bases times the height over 2. And we know that the two bases must be parallel to each other. Here, side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that we know that ABSD is a rectangle, and we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. But DS is part of the straight line DC and is parallel to AB. So if a part of a straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line AB. So in conclusion, we found that DC is parallel to AB, and therefore the two bases of this trapezoid ABCD are AB and DC. And therefore the sum of the two bases is AB plus DC. and the area of trapezoid ABCD equals to the sum of the two bases times the height over 2. The height must create 90 degrees with the two bases. Here you can see that side AD creates 90 degrees with the base AB, and it also creates 90 degrees with the base DC. Therefore, the height is AD divided by 2. In conclusion, we found out that the area of trapezoid ABCD equals to the sum of the two bases of trapezoid ABCD, that is to say AB plus DC, times the height, that is AD over 2. AB equals to x plus DC is equals to 7 over x times the height AD equals to A according to our definition, divided by 2. So in conclusion, we found out that area of trapezoid ABCD equals to x plus 7 over x times A over 2. But according to equation 1, this is equation 1, x plus 7 over x equals to A plus B. Therefore, we can substitute x plus 7 over x here by A plus B. We'll do it now. So x plus 7 over x is A plus B. And we have to multiply it by A and divide it by 2. So in conclusion, we found out that the area of trapezoid ABCD equals to A plus B times A over 2. Here we will open the brackets of this expression, and we get that A times A is A squared plus AB over 2. But A squared plus AB according to this equation 2 equals to 14. Again, A squared plus AB equals to 14 according to this equation 2. Therefore, we can substitute A squared plus AB in this equation by 14. We will do it now. So in total, this expression equals to 14 over 2. That is 7. In conclusion, we found out that the area of trapezoid ABCD is equals to 7 square units. Repeat again. The area of this trapezoid ABCD equals to 7 square units. In the next step, I will present to you the second question. So, in the drawing we have rectangle ABCD. Inside this rectangle ABCD, we have, in addition, we know that side CB of this rectangle ABCD equals to 7 units in length. This is side CP that equals to 4 units in length. This is side PQ that equals to 2 units. And this is side AQ that is equal to 5 units in length. In addition, we know that this is angle CPQ, that is a right angle, and this is angle PQA, that is also a right angle. Our mission in question 2, the second question, is to find out the area of this green shape. Okay, so first of all, we will join points C and A together by a straight line. we will define the intersection point of diagonal CA with plane segment PQ. This point is point M. We know that line segment PQ equals to 2. We define the length of this line segment PM as X. So what is the length of this line segment MQ? From the drawing, it is very easy to see that MQ equals to PQ minus PM. Again, MQ equals to PQ minus PM. So write it down. MQ equals to PQ minus PM. So MQ equals to PQ, that is 2 according to what is given as the question, minus PM. PM equals to X according to our definition. So in total, MQ equals to 2 minus X. So MQ equals to line segment MQ equals to 2 minus X. Actually, by doing this construction, we can add here those two vertex angles. Angle AMQ is defined as vertex angle, and the second vertex angle is angle PMC. This is angle PMC that is also defined as a vertex angle. And you know that vertex angles are equal to each other. So if angle AMQ, the vertex angle AMQ equals to theta, then the other vertex angle PMC must be also equal to theta. Okay. In the next step, we will focus on this right triangle AMQ. This right triangle AMQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, according to the same logic, if we focus on this right small green triangle CPM, on this small right triangle CPM, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing square, the angle must be equal to 90 degrees minus theta. In the next step, we will prove that those two right triangles are similar to each other. That is to say, we will prove that the right triangle AMQ, the right white triangle AMQ, is similar to the right small green triangle PMC. So I write it down. We prove that the right white triangle AMQ is similar to this right green small triangle PMC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. So this is angle AMQ. in the right triangle AMQ, and it is equals to this angle, that's the angle CMP, in the right green triangle PMC. Repeat again. Angle AMQ in the right triangle AMQ equals to angle CMP in the right triangle PMC. They are both equal to theta, therefore they are equal to each other. In addition, those two angles, they are both right angles, they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle MQA. In the right triangle AMQ, the right triangle AMQ, and it is equals to this angle, that is actually angle MPC. In the right green triangle PMC. Repeat again. Angle MQA in the right triangle AMQ equals to angle MPC in the right triangle PMC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle MAQ in the right triangle AMQ, and it is equals to this angle. This is actually angle PCM in the right green triangle PMC. Repeat again. Angle MAQ in the right triangle AMQ, the right triangle AMQ, equals to angle PCM in the right green triangle PMC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the right triangle AMQ are correspondingly equal to all the three angles in this right green small triangle PMC. And therefore we actually proved that those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually proved that the right triangle AMQ is similar. This is the sign of similar to the right green small triangle PMC according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PM in the right green small triangle PMC over side MQ in the right white triangle AMQ is equals to side CP in the right green small triangle CPM over side AQ in the right white triangle AMQ. Repeat again. We derive that PM over MQ equals to CP over AQ. PM equals to X over MQ. MQ equals to 2 minus X. And it is equals to CP. CP is 4 over AQ. AQ is 5. So in conclusion, we should find out that x over 2 minus x equals to 4 over 5, or 4 fifths. Here we cross multiply this equation, and we get that 5x equals to 4 times 2 minus x. So here we open the brackets on this side of the equation, and we get that 5x equals to 4 times 2 is 8, and 4 times minus x is minus 4x. So if we found out that 5x equals to 8 minus 4x, here we add 4x to this equation, and we get that 5x plus 4x is 9x, so 9x equals to 8. Here we divide this equation by 9, and finally we get that x equals to 8 over 9, or x equals to 8 ninths. So 9:07 p.m. that is equal to x according to our definition is equals to 8 ninths. So what is the length of 9/7 mq? 9/7 mq equals to 2 minus x. 2 is 18 ninths, and therefore 2 minus x is 18 ninths minus x. And x is 8 ninths, so in total 2 minus x equals to 18 ninths minus 8 ninths. 18 ninths minus 8 ninths equals to 10 ninths. So in conclusion, we found out that PM equals to 8 ninths and MQ equals to 10 ninths. Okay. In the next step, I will copy this line AQPC in a new page, and we will analyze this line AQPC. It is given as the equation that line segment AQ equals to 5 units in its length. And this is angle AQP, that is a right angle. Line segment PQ equals to 2 units in its length. This is angle CPQ, that is also a right angle. And finally, line segment CP equals to 4 units in its length. So actually, this is the straight line. It is not a straight line, of course. This is line AQPC that I got it from the original drawing. So in the next step, we will extend the straight line AQ by straight line. When you extend the straight line by straight line, the result must be a straight line. So this is a straight line. So if you focus on the upper side of this straight line, it's point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line, equals to 180 degrees. So here we can say that the sum of the angles on the upper side of this straight line at point Q must be equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle, that is a right angle, plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say from point C we draw perpendicular on the extended AQ. Again, from point C, we draw perpendicular on the extended AQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C in the extended AQ, this point Sn. By doing this construction, we get the quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. So inside quadrilateral PC and Q, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we relate to this quadrilateral PC and Q as a rectangle. Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PQ must be equal to the opposite side CN. But PQ is 2, therefore CN is also 2. Likewise, according to the same rule, in the same rectangle PC and Q, side PC must be equal to the opposite side QN. But PC is 4, therefore QN is also 4. In the next step, we will join points A and C together by a straight line. By joining points A and C, we can get the right angle ACN. So in the next step, we will implement the Pythagoras theorem on this right angle, triangle ACN. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right angle ACN is AC, therefore the square of the hypotenuse is AC square. And it must be equal to CN square plus AN square. So AC square equals to CN square plus AN square. AC square, this is the square of the hypotenuse, equals to CN square. CN is 2, therefore CN square is 2 squared, that is 4, plus AN square. AN in total equals to 5 plus 4, that is 9, and therefore AN square is 9 squared, that is 81. So in total we can find out that AC square equals to 4 plus 81, that is 85. So AC square equals to 85. It is given us the question that ABCD is a rectangle, and we know that all the angles inside any rectangle are right angles. Therefore, this is angle ABC, that is a right angle. In the next step, I will copy this right big triangle ABC in a new page, and we will implement the Pythagoras theorem in this right triangle, the right big triangle ABC. Here by PT is the abbreviation for Pythagoras theorem. side CB of rectangle ABCD equals to 7, therefore side CB of the rectangle ABC equals to 7 units in its length. We just right now found out that AC squared equals to 85. That is to say, the square of the hypotenuse AC squared in the rectangle ABC is 85. Currently, this is the rectangle triangle ABC that I covered from the original drawing. So according to the Pythagoras theorem, in this rectangle ABC, AC squared equals to AB squared plus CB squared. AC squared is 85 and it equals to AB squared. AB is the missing side, so we leave it as it is. Plus CB squared. CB is 7, therefore CB squared is 7 squared, that is 49. Here we subtract 49 from this equation, and we get that AB squared equals to 85 plus 49 is 36. So AB squared equals to 36. We take a root from this equation, and we get that AB equals to the square root of 36, that is 6. So here AB, this is side AB, that equals to 6 units in its length. I repeat again that our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the big right triangle ABC. But the problem is that the area of the big right triangle ABC consists of this white triangle AMQ, and we are interested only on the green area. So we have to subtract from the area of triangle ABC the area of this right triangle AMQ. But the area of triangle ABC doesn't include the area of this small right triangle PCM. Therefore, we have to add to the area of this triangle ABC the area of this right triangle PCM that is not included in the area of triangle ABC. So if we found out that the area of the green shape in total equals to the area of the green of the right big triangle ABC minus the area of the right triangle MQA plus the area of the right small green triangle PCM. I repeat again. The area of the green shape in total equals to the area of the right big triangle ABC minus the area of the right white triangle AMQ plus the area of the right small green triangle PCM. What is the area of triangle ABC? The area of triangle ABC equals to the base of the triangle, that is AB, times the height to the base, that is BC, over 2. Repeat again. The area of the right big triangle ABC equals to the base AB times the height to the base, that is BC, over 2. Minus the area of the right triangle AMQ. What is the area of the right triangle AMQ? It equals to the base of the triangle, that is AQ, times the height to the base, that is MQ, over 2. Repeat again. the area of the right triangle AMQ equals to AQ times MQ over 2, plus the area of the green small right triangle PCM. What is the area of this green small triangle PCM? This equals to the base of the triangle, that is PC, times the height to the base, that is PM, over 2. Repeat again, the area of the right green small triangle PCM equals to PC times PM over 2. So the area of triangle ABC equals to AB times BC over 2. AB is 6 times BC is 7 over 2. So if we found out that in total the area of the right big triangle ABC equals to 6 times 7 over 2, minus the area of the right triangle AMQ. The area of triangle, the right triangle AMQ equals to AQ. AQ is 5 times MQ. MQ is 10 times, divided by 2. So in total we actually found out that the area of the right triangle AMQ equals to 5 times 10 over 2 times 9, plus the area of the right green small triangle PCM. The area of the right small green triangle PCM equals to PC is 4 times PM. PM is 8 nines, divided by 2. In conclusion, we found out that the area of the right green small triangle PCM equals to 4 times 9 over 2 times 9. So the area of the big right triangle ABC equals to 6 times 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So the area of the triangle ABC equals to 21 square units, minus the area of the right triangle AMQ. This equals to this expression. Here we have 10 over 2 is 5, and 5 times 5 is 25, so in total this expression equals to 25 over 9. So the area of the right triangle AMQ equals to 25 over 9 square units, plus the area of the right green small triangle PCM is equals to this expression. Here we have 8 over 2 is 4, and 4 times 4 is 16. So in total this expression equals to 16 over 9. So the area of the right green small triangle PCM equals to 16 over 9 square units. So here the area of the green shape equals to 21. Here we have minus 25 plus 16 over 9. So the area of the green shape equals to 21. And here minus 25 plus 16 is minus 9. So in total this expression equals to minus 9 over 9. So the area of the green shape equals to 21 minus 9 over 9. Minus 9 over 9 is minus 1. So the area of the green shape equals to 21 minus 1. 21 minus 1 is 20. So in conclusion, we found out that the area of the green shape equals to 20 square units. Repeat again. The area of this green shape equals to 20 square units. So in the next step, I will summarize the lecture. We start with the first question. our mission in the first question was to find out the area of this trapezoid ABCD. So in the drawing we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that this is side AB that is equals to x units in length. This is side DC, trapezoid ABCD, that is equals to 7 over x units in length. This angle BAD is a right angle, and this angle ADC is also a right angle. And repeat again, our mission is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. I repeat again, a trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD, and because of the fact that side AB is parallel to side DC, this quadrilateral ABCD is defined as a trapezoid. So this is trapezoid ABCD. The two parallel sides, that is to say AB and DC, are defined as the bases of this trapezoid. So the base AB equals to B according to our definition, the base DC equals to A according to our definition. So what is the area of this trapezoid ABCD? The area of the trapezoid ABCD equals to the sum of its two bases, that is to say B plus A or A plus B, times the height over 2. Repeat again, the area of trapezoid ABCD equals to A plus B times h over 2. The height h must create 90 degrees with the two bases. And indeed, the height h creates 90 degrees with the base AB, and it creates also 90 degrees with the base DC. And therefore, here, h is the height to the base. So in total, there are, in conclusion, we found out that the area of this trapezoid ABCD equals to A plus B times h over 2. So in the first step, we defined the points of tangencies of this trapezoid ABCD with this circle with letters. We defined the point of tendency of tangent AB with this circle, this point as E. We defined the point of tendency of this tangent AD with this circle, this point as G. We defined the point of tendency of this tangent BC with this circle, this point as F. And finally, we defined the point of tendency of this tangent DC with this circle, this point as H. So here we can implement rule 2. I'm going quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the domain we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, rule 2, they are equal to each other. That is to say, PA equals to PB. We can definitely implement rule 2 in our drawing. Why? Because in our drawing, we have the common external point, point A. From this common external point, point A, we have two tangents to this circle, tangent AE and tangent AG. And according to rule 2, they are equal to each other. That is to say, AE equals to AG. So if we define the length of this tangent AE as y, then the length of tangent AG must be also equal to y according to rule 2. Likewise, if you focus on this common external point, point B, on this common external point, point B, we have two tangents to this circle, tangent BE and tangent BF. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of this tangent BE as Z, then the length of this tangent BF must be also equal to Z according to rule 2. Likewise, if we focus on this common external point, point C, from this common external point, point C, we have two tangents to this circle, tangent CF and tangent CH. And according to rule 2, they are equal to each other. That is to say, CF equals to CH. So if we define the length of this tangent CF as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, if we focus on this common external point, point D, from this common external point, point D, we have two tangents to this circle, tangent DG and tangent DH. And according to rule 2, they are equal to each other. That is to say, DG equals to DH. So if we define the length of this tangent DG as T, then the length of this tangent DH must be also equal to T according to rule 2. In the next step, we define the length of this side AD of trapezoid ABCD as A, and we define the length of this side BC of trapezoid ABCD is B. So what is the value of AB plus DC? AB equals to Y plus Z. DC equals to T plus M. And therefore in total AB plus DC equals to Y plus Z plus T plus M. Likewise, we added side AD to the opposite side BC. So what is the value of AD plus BC? AD is Y plus T plus BC, that is Z plus M. So in total AD plus BC, AD plus BC in total equals to Y plus T plus Z plus M. According to the algebraic identity that A plus B equals to B plus A, we can change the orders of the letters of this expression. That is to say, instead of Y plus D plus Z plus M, we can write that this expression equals to Y plus Z plus T plus M. We just change the orders. So we actually found out that AB plus DC equals to Y plus Z plus T plus M, and AD plus BC also equals to Y plus Z plus T plus M. So those two expressions in the green color, they are both equal to the same third expression, that is Y plus Z plus T plus M, and therefore they are equal to each other. That is to say, AB plus DC equals to AD plus BC. This is equation 1. AB equals to X according to what is given as the equation. DC also equals to DC equals to 7 over X, also according to what is given as the equation. AD equals to A according to our definition. BC equals to B according to our definition also. So according to equation 1, we actually found out that X plus 7 over X equals to A plus B. In the next step, we did a construction, that is to say, from point B, we draw perpendicular on DC. Again, from point B, we draw perpendicular on side DC of trapezoid ABCD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC, this point as point S. By doing this construction, we added a quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, the sum of those 4 angles must be equal to 360 degrees. That is the sum of the angles in any quadrilateral. Therefore, the fourth missing angle must be equal to 90 degrees in its size. Why? Because 270 degrees, that is the sum of the 3 angles plus the size of this angle, that is 90 degrees. It is 360 degrees. That is the sum of the angles in any quadrilateral. So inside quadrilateral ABSD, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we relate to this quadrilateral ABSD as a rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to the opposite side DS. But AB equals to X, therefore DS must be also equal to X. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But AD equals to A, therefore BS must be also equal to A. By doing this construction, we created the right triangle BSC. In the right triangle BSC, we already found out that side BS equals to A, the hypotenuse BC equals to B. So what is the length from side SC? From the drawing, it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. So SC equals to DC, that is 7 over X, minus DS, that is X. So in total, SC equals to 7 over X minus X. In the next step, I copied this right triangle BSC in a new page and we implemented the Pythagoras theorem on this right triangle BSC. So actually, this is the right triangle BSC that I copied from the original drawing. According to the, here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle BSC is BC, therefore the square of the hypotenuse is BC square, and it must be equal to BS square plus SC square. BC is B, therefore BC square is B square, and it is equal to BS square. BS is A, therefore BS square is A square, and plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. So here, according to equation 2, we actually found out that B square equals to A square plus 7 over x square. Here we have the expression of 7 over x minus x square. But our mission is to turn this expression to the expression of 7 over x plus x. This is equal to a plus b according to equation 1. In order to turn this expression from 7 minus x, from 7 over x minus x to 7 over x plus x, we use the algebraic identity that states that a minus b square equals to a plus b square minus 4 times ab. So according to this algebraic identity, we get that 7 over x minus x square will be equal to 7 over x plus x square minus 4 times 7 over x minus x. Here we have x square on both. We have x on both sides of the equation, of this expression. So x, we have x in the numerator and x in the denominator. So x will get cancelled, and therefore in total this expression will be equal to minus 4 times 7, that is minus 28. So the expression 7 minus x, 7 over x minus x square, according to this algebraic identity, equals to 7 over x plus x square minus 28. Therefore, we can substitute 7 over x minus x square in this equation 2 by 7 over x plus x square minus 28. We did it and found out that according to equation 2, b square equals to a square, and 7 over x minus x square equals to 7 over x plus x square minus 28 according to this algebraic identity. So according to equation 2, actually found out that b square equals to a square plus 7 over x plus x square minus 28. Here we open the brackets of this expression. Actually, 7 over x plus x according to equation 1 equals to a plus b. Repeat again. 7 over x plus x equals to a plus b. So if 7 over x plus x equals to a plus b, it means that 7 over x plus x squared will be equal to a plus b squared. Therefore, substitute 7 over x plus x, 7 over x plus x squared in this equation 2 by a plus b squared. So in total, according to equation 2, we actually found out that b squared equals to a squared plus a plus b squared minus 28. This is according to equation 2. Here we open the brackets of this expression a plus b squared, and finally found out that according to this equation 2, b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab, and we have to add also minus 28, that is in the equation 2. So here we have b squared on both sides of the equation, so b squared will get cancelled. After we cancel b squared, in this side of the equation we have nothing, that is to say 0. So it is equal 0 equals to a squared plus a squared is 2a squared plus 2ab minus 28. Here we added 28 to this equation 2, and found out that 0 plus 28 is 28. This equals to 2a squared plus 2ab. So according to equation 2, 28 equals to 2a squared plus 2ab. Here we divided this equation 2 by 2. So 28 over 2 is 14, 2a squared over 2 is a squared, plus 2ab over 2 is ab. So in total, actually found out that according to equation 2, 14 equals to a squared plus b squared. This is according 14 equals to a squared plus ab. This is according to equation 2. But according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have here those two equations. Our mission is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two bases times the height over 2. And we know that the two bases must be parallel to each other. Here we know that actually side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that ABSD is a rectangle, and you know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB must be parallel to the opposite side DS. AB is parallel to DS, but DS is part of the straight line DC and is parallel to AB. So if a part of the straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line that is AB. So in conclusion, actually found out that DC is parallel to AB. And therefore the two bases of trapezoid ABCD are DC and AB, and therefore the sum of the two bases is DC plus AB. Or AB plus DC. Again, the sum of the two bases is AB plus DC times the height. The height must create 90 degrees with the two bases. And AD creates 90 degrees with the base AB. This angle equals 90 degrees. And it also creates 90 degrees with the base DC. This angle also equals to 90 degrees. Therefore, the height is AD. So it is times the height AD over 2. So the area of trapezoid ABCD equals to the sum of the two bases, that is AB plus DC, times the height, that is AD over 2. AB is x, DC is 7 over x, AD is A, divided by 2. So we have here x plus 7 over x. But according to equation 1, x plus 7 over x equals to A plus B. So we can substitute x plus 7 over x by A plus B. We did it. So x plus 7 over x is A plus B. We have to multiply it by A over 2. We open the brackets of this expression. A plus B times A is A times A is A squared plus AB divided by 2. But A squared plus AB, according to this equation, equation 2, A squared plus AB equals to 14. Therefore we can substitute A squared plus AB, this expression, by 14. We did it. So this expression in total equals to 14 over 2. 14 over 2 is 7. So if we found out that the area of trapezoid ABCD equals to 7 square units. I repeat again, the area of this trapezoid ABCD equals to 7 square units. Okay, so we finish with the first question. The next step I actually presented to you, the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that side CB of rectangle ABCD equals to 7 units in length. In addition, inside rectangle ABCD we have here side CP that is equals to 4 units in length. Side PQ equals to 2 units in length. Side QA equals to 5 units in length. This is angle CPQ, that is a right angle. This is angle PQA, that is also a right angle. Again, our mission is to find out the area of this green shape. So in the first step, we joined point C and A together by a straight line. And we defined the intersection point of diagonal CA with line segment PQ, this point as M. We know that PQ equals to 2 units in length. We define this line segment PM as X. So what is the length of MQ? From the drawing it is very easy to see that MQ equals to PQ minus PM. Repeat again, MQ equals to PQ minus PM. So MQ equals to PQ, that is 2, minus PM, that is X. So in conclusion, we found out that MQ equals to 2 minus X. And PM equals to X according to our definition. The next step, we focus on this right triangle AQM. But before that, by doing this construction, we created here two vertex angles, and we know that vertex angles are equal to each other. Those two angles are vertex angles and they are equal to each other. So if this angle is theta, then this angle must be also equal to theta. In the next step, we focus on this right triangle AMQ. In this right triangle AMQ, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees, that is the sum of the angles in any triangle. Likewise, according to the same logic, in the small green triangle PCM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle must be equal to 90 degrees minus theta. In the next step, we proved that those two right triangles are similar to each other. That is to say, the right triangle AQM is similar to the right green small triangle PCM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in this right triangle AQM are correspondingly equal to all the three angles in the right small green triangle PCM, this right green small triangle PCM, and therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PM in the right triangle PCM over side MQ in the right triangle AMQ is equals to side PC in the right triangle PCM over side AQ in the right triangle AMQ. Repeat again, we derive that PM over MQ equals to CP over AQ. PM is X, MQ is 2 minus X, MQ is 2 minus X, CP is 4, AQ is 5. So in conclusion, we should found out that X over 2 minus X equals to 4 over 5. Here we just multiply this equation, and finally found out that 5x equals to 4 times 2 minus x. Here we open the brackets on this side of the equation, and found out that 5x equals to 4 times 2 is 8, and 4 times minus x is minus 4x. So in conclusion, we found out that 5x equals to 8 minus 4x. Here we added 4x to this equation, and found out that 5x plus 4x is 9x, so 9x equals to 8. Here we divided this equation by 9, and finally found out that x equals to 8 ninths. So this is 9:70 p.m. is equal to x is equal to 8 ninths. And here mq equals to 2 minus x. 2 is 18 ninths, so 2 minus x is 18 ninths minus x. That is to say, it is 18 ninths minus x, that is 8 ninths. And 18 ninths minus 8 ninths is 10 ninths. So we found out that mq equals to 10 ninths and pm equals to 8 ninths. In the next step, I copied this straight line, it is not a straight line, I copied this line CPQ, I copied this line AQPC, and then you page and analyze this line AQPC. This is line AQPC, that I wrote on the original drawing. AQ equals to 5, this is a right angle. PQ equals to 2, PC equals to 4, and this is also a right angle. In the next step, I actually extended the straight line AQ by straight line, and we got this, when you extend the straight line by straight line, the result is a straight line. So this is a straight line. If you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to rule 3, that the sum of the angles to one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line at point Q? We have this angle, that is the right angle, plus this vicinal in total they must be equal to 180 degrees. Therefore, this vicinal must be equal to 90 degrees in its size. In the next step, we did the construction, that is to say from point C, we do perpendicular on the extended AQ. Again, from point C, we do perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C in the extended AQ, this point is N. By doing this construction, we created here quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing again, total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing again must be equal to 90 degrees in its size. So inside quadrilateral PC and Q, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral PC and Q as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PC equals to the opposite side QN. But PC is 4, therefore QN must be also equal to 4. Likewise, according to the same rule, in the same rectangle PC and Q, side PQ must be equal to the opposite side PN. But PQ is 2, therefore CN must be also equal to 2. In the next step, we join points A and C together by straight line. By joining points A and C, we created the right triangle, triangle ACN. So we implemented the Pythagoras theorem in this right triangle ACN. According to the Pythagoras theorem, in the right triangle ACN, AC square equals to CN square plus AN square. So AC square equals to CN square. CN is 2, therefore CN square is 2 square, that is 4, plus AN square. AN in total equals to 5 plus 4, that is 9, therefore AN square equals to 9 square, that is 81. So in total we found out that AC square equals to 4 plus 81, that is 85. So AC square, that is the square of the hypotenuse, of the right triangle CN equals to 85. It is given us the question that ABCD is a rectangle, and you know that all the angles inside any rectangle are right angles. And especially this angle ABC is a right angle. So I copied the right triangle ABC in a new page and we implemented the Pythagoras theorem in this right triangle, triangle ABC. So this is the right triangle ABC that I copied from the original domain. Side BC equals to 7 inches according to what is given us the question. And we just right now found out that AC square equals to 85. Yeah, AC square equals to 85. So according to the Pythagoras theorem, in this right triangle ABC, AC square equals to AB square plus BC square. AC square is 85, and it is equals to AB square. AB is the missing side, so we leave it as it is, plus CB square. CB is 7, therefore CB square is 7 square, that is 49. So we found out that 85 equals to AB square plus 49. Here we subtracted 49 from this equation, and finally found out that AB square equals to 85 minus 49 is 46. So AB square equals 85 minus 49 is 36. So we found out that AB square equals to 36. Here we took out of this equation and finally found out that AB equals to the square root of 36, that is 6. So AB equals to 6. This is side AB is equal to 6, and it is given as the equation that side BC equals to 7. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the right big triangle ABC. But because of the fact that the area of the big right triangle ABC includes also the area of the white right triangle AMQ, and we are interested only on the green area, we have to subtract from the area of triangle ABC the area of this right triangle AMQ, and because of the fact that the area of triangle ABC doesn't include the area of this small green right triangle PCM, we have to add to the area of triangle ABC the area of this small green right triangle PCM. So in conclusion, we found out that the area of the green shape in total equals to the area of triangle ABC minus the area of the right triangle AMQ plus the area of triangle PCM, the right green small triangle PCM. Repeat again, the area of the green shape in total equals to the area of the big right triangle ABC minus the area of the right triangle AMQ plus the area of the green small right triangle PCM. The area of the triangle ABC equals to the base that is AB times the height of the base that is BC over 2. Minus the area of the triangle AMQ. Area of the triangle AMQ equals to the base that is AQ times the height of the base that is QM over 2. Repeat again, the area of the green white triangle, the area of the white triangle AMQ equals to the base that is AQ times the height of the base that is MQ over 2. And finally, plus the area of triangle PCM. The area of the right green triangle PCM equals to the base that is PC times the height of the base that is PM over 2. Repeat again, the area of the green small right triangle PCM equals to the base that is PC times the height of the base that is PM over 2. So the area of triangle ABC equals to AB times BC over 2. AB is 6, BC is 7, divided by 2. So in total, the area of triangle ABC equals to 6 times 7 over 2, minus the area of the right triangle AMQ, that is AQ times MQ over 2. AQ is 5, MQ is 10/9 divided by 2. So in total, the area of the right triangle AMQ equals to 5 times 10 over 2 times 9, plus the area of the white small green triangle PCM is equals to PC times PM over 2. PC is 4, PM is 8/9 divided by 2. So in total, the area of the right green small triangle PCM equals to 4 times 8 over 2 times 9. So the area of triangle ABC equals to 6 times 7 over 2, that is 21. This expression 5 times 10 over 2 times 9 equals to minus 5 times 10 over 2 times 9 equals to minus 25 over 9. And this expression 4 times 8 over 2 times 9 in total equals to 16 over 9. So in conclusion, we actually found out that the area of the green shape equals to 21 minus 25 over 9 plus 16 over 9. So it is 21, and here we have minus 25 plus 16 is minus 9 divided by 9. So in total, this expression equals to minus 9 over 9. So the area of the green shape equals to 21 minus 9 over 9. Minus 9 over 9 is minus 1. So in total, the area of the green shape equals to 21 minus 1, that is 20. So in conclusion, we actually found out that the area of this green shape equals to 20 square units. Okay, thank you very much.